Amid the freezing lands of northern Sweden, humans have carved a pit approximately 450 meters deep into the earth. This is Aitik, one of the largest open-pit copper mines in Europe, where rock layers millions of years old are stripped away to supply metal for modern industry. But nature did not give Aitik rich copper veins. The ore here contains only about 0.2% copper. This means that, to obtain a relatively small amount of metal, Aitik must excavate, transport, crush, and process nearly 40 million tons of ore every year. So how has Aitik turned a low-grade ore body into the largest copper mine in Europe? Join Mandarin Tech as we go deep into the operating process of this gigantic mining machine. Located near the town of Gällivare, Sweden, Aitik is one of Europe's most important copper mining centers. The ore body was discovered in the 1930s, but large-scale mining did not truly begin until 1968. Initially, it was a mine that was difficult to make profitable because the copper was spread too thinly through the rock. Faced with this disadvantage, Boliden, a Swedish mining and metals company, adopted a long-term vision. Rather than searching for richer ore, it built a vast mining and processing system capable of operating continuously with high precision to turn low-grade ore into valuable products. Every year, Aitik mines approximately 45 million tons of ore, containing around 97,000 tons of copper, along with small amounts of gold and silver. That copper then enters power grids, wind turbines, electric vehicles, and digital infrastructure. It is present in nearly every link of the modern economy, while also becoming one of the key materials driving Europe's green transition. Amid the freezing landscape, Aitik opens like a colossal cut in the earth, stretching nearly 3 kilometers, measuring about 1 kilometer wide, and reaching approximately 450 meters below the surface. To establish figures of this scale, geologists had to trace each rock core to map precisely the copper hidden underground. Drilling rigs extract cylindrical rock cores, recording the geological structure through every color, fracture, and mineral band. The inclination of each borehole is measured using gyroscopic equipment, because even a small deviation at depth can shift the position of the ore body on the map by several meters. The rock cores are then cut into samples and sent to a laboratory to determine their copper, gold, and silver content, along with associated elements. Behind Aitik's geological map lies an immense database, more than 1,100 boreholes, with a total length exceeding 400 kilometers and approximately 75,000 composite samples analyzed. From these scattered data points, engineers construct a three-dimensional model of the underground geology and divide it into blocks measuring approximately 20 by 20 by 15 meters. Each block is assigned information about rock type, density, and estimated metal content, helping the operating team determine which blocks of rock should enter the ore processing system and which should be sent to the waste dump. Once the ore boundaries have been established, the mining bench is leveled so that the large drilling rigs can move in. They travel along a predetermined grid, lower their drill bits into the rock, and create a series of deep vertical holes through the entire layer of material to be removed. The spacing between the blast holes is calculated according to the hardness and structure of the rock. If the holes are placed too far apart, they will produce oversized rocks that are difficult to crush, while placing them too close together wastes explosives and may damage the pit walls. At Aitik, production blast holes are approximately 31 centimeters in diameter, and each hole can contain nearly 1 ton of explosives. Near the pit walls, smaller holes are drilled at closer spacing and loaded with limited amounts of explosives to create a clean cut without fracturing the rock that must remain intact. After the explosives have been loaded and the mouths of the holes sealed, the system detonates each row in sequence at delays measured in milliseconds. The blast waves cause the rock mass to lose its support, collide, and collapse into loose material instead of being thrown outward in a single, uncontrolled explosion. Once the dust has settled, the technical team checks for oversized rocks, undetonated holes, and the stability of the bench walls. Only after the area has been confirmed safe can excavators and haul trucks move in, carrying the ore and waste rock in separate directions. Across the mining bench covered with fragmented rock, enormous electric shovels begin loading the material onto haul trucks, creating a continuous flow from the bottom of the pit to the crushing station. The enormous bucket digs into the chaotic mass of material, lifts each load of rock, and empties it into the truck waiting beside it. Ore and waste rock may lie close together on the same mining bench, so every bucket load at Aitik must be placed into the correct designated truck. The geological map within the dispatch system shows the location of each shovel, the type of material, and its corresponding dumping point. Every year, approximately 70 million tons of rock move through this pit. To control this immense flow of material, the control room tracks the position of the vehicles, assigns trucks to each shovel, and continuously adjusts their routes. Ore is hauled to the crusher, while waste rock is diverted to separate storage areas or reused to build roads and reinforce working surfaces. The greatest challenge appears on the uphill journey. A Caterpillar 795F can carry up to 313 tons of rock, turning every climb from the bottom of the pit into a battle between gravity and fuel. At the receiving station, the truck body rises and dumps hundreds of tons of rock into the hopper with a violent crash. Oversized rocks are broken down, while the remaining material falls into the primary crusher, bringing its journey through the mining area to an end and beginning the process of separating copper from rock. After leaving the primary crusher, the ore is smaller, but the copper remains locked within the rock structure. Therefore, to release the metal, it is transported to the processing plant and broken down to a scale that is almost impossible to distinguish with the naked eye. The ore first enters an autogenous mill, a gigantic steel drum rotating slowly around its axis, where the rocks collide with one another and with the walls of the mill, causing them to break into smaller pieces. The material is then ground a second time in a pebble mill, mixed with water to form a slurry, and classified. Particles that have reached the required fineness move to the next stage, while the coarser material is returned for further grinding until it reaches the necessary fineness. After grinding, the ore slurry is transferred into flotation tanks. Here, chemicals make the surfaces of the copper minerals more likely to attach to air. Millions of tiny bubbles rise, carrying the metal-bearing particles and gathering them into a dark layer of froth on the surface. Worthless rock sinks to the bottom and separates from the product stream. The copper-rich froth is collected, passed through a thickener, and then pressed through an air pressure filter to remove water. Gold and silver also follow this concentrate stream. The waste slurry is divided into high sulfur and low sulfur groups before being transferred to separate storage areas. The final product is not yet bright red copper sheets, but a dark mineral powder containing the valuable material extracted from the rock. It is transported to the railway station within the mine, loaded onto trains, and sent to the Rönnskär smelter for further refining. After leaving Aitik, the copper concentrate is transported to the Rönnskär smelter. There, the dark mineral powder is dried and then fed into a high-temperature furnace, causing the copper-bearing minerals to melt and separate from the impurities. The molten metal is further processed to remove iron and sulfur before being cast into crude copper anode plates. The anode plates are then suspended alternately with cathodes in electrolytic tanks. Under the effect of an electric current, copper leaves the anodes, moves through the solution, and gradually deposits on the cathode surfaces as a layer of pure metal. The remaining impurities settle at the bottom of the tanks, where they may contain gold and silver for separate recovery. At the end of the journey, the copper, once thinly dispersed through the rock, has become cathode plates ready to enter modern industry. Thanks to the closed-loop recovery process, nearly all the metal value hidden within the material stream is retained before the remaining material leaves the production line. At Aitik, size is not for show, it is a condition for survival. Standing out across the mining benches is the P&H 4100 XPC, an electric rope shovel weighing approximately 1,600 tons, equivalent to more than 1,000 passenger cars, and standing nearly 15 meters tall, comparable to a 5-story building. At the front is a bucket with a capacity of 45 cubic meters, large enough to swallow dozens of tons of rock each time it is lowered. After only a few passes, the bed of a mining truck is full. When operating continuously, the machine can handle up to 6,000 tons of material per hour. The P&H 4100 XPC does not carry a gigantic diesel engine. It receives 6,600 volts of electricity through a high-voltage cable system, then converts the current into enough pulling force to tear entire sections of rock from the bench face. Each time the steel bucket bites into the ground, the entire machine trembles like a living structure digging deep into the mine. In the world of open-pit mining, the Bagger 293 is one of the most extreme machines ever built. It is approximately 225 meters long, nearly 96 meters tall, and weighs up to 14,200 tons. At the front is a bucket wheel, measuring more than 21 meters in diameter and carrying 18 steel buckets, capable of excavating up to 240,000 cubic meters of material every day. Once cut from the surface, the earth and rock are immediately discharged onto the conveyor system, creating an almost continuous flow of material. Following the giant excavators is a fleet of mining trucks so large that a fully grown adult reaches only as high as the center of a wheel. The Caterpillar 795F is 15 meters long, 9 meters wide, weighs approximately 250 tons when unladen, and has a rated payload of 313 tons. Each tire alone measures more than 4 meters in diameter. The fleet of Komatsu 930E-5 trucks is equally massive, with a payload of approximately 290 tons and a height of more than 7 meters. Boley then states that Aitik operates approximately 30 mining trucks and has invested in automating 11 Komatsu trucks, together with a new control room. Instead of each vehicle operating as a separate unit, the entire fleet is gradually becoming a network, receiving commands, maintaining distance, and adjusting its route according to a shared plan. In a mine that must move enormous volumes of material, a few seconds saved in each cycle can add up to thousands of operating hours. Therefore, Aitik does not simply increase the size of its machinery. The mine also gives the machines the ability to work autonomously. The Pit Viper drill rigs are connected to a remote control room. Operators can sit inside an office building and monitor data on screens instead of directly facing the noise, rock dust, and snowstorms on the mining benches. In semi-autonomous mode, a drill rig can move between positions by itself and complete an entire row of holes after receiving the start command. Under favorable conditions, this technology has increased equipment utilization from approximately 45 to 50% to 80%, while raising productivity by approximately 30%. At Aitik, the presence of copper in the rock is not necessarily enough to make it ore. Each block of material must pass a strict calculation. The amount of recoverable metal must exceed the total cost of drilling and blasting, loading, transport, grinding, flotation, and waste treatment. Otherwise, it is still excluded from the plan, even though copper remains inside. Therefore, Aitik does not apply a single fixed threshold across the entire mine. Depending on the location and mining conditions, the economic cutoff ranges from approximately 0.04% to 0.14% copper. Rock hardness also determines profitability. Rock types such as diorite and aplite require more energy to grind, increasing processing costs in the economic model by approximately 20%. As a result, two blocks of rock containing similar amounts of copper can still have completely different values. Aitik counters low-grade ore through scale. Every small saving, when multiplied across millions of tons of material, becomes a major advantage. However, a decline of only a few percentage points in recovery efficiency can cause a significant amount of metal to be lost in the waste stream. Geology remains almost unchanged, but the boundary of profitability constantly shifts with metal prices, technology, and energy costs. As high-grade ore bodies become increasingly difficult to find, Aitik has become a reference model for the next generation of mines. When scale, technology, and operational management are combined precisely, even low-grade ore can become the foundation of a profitable and sustainably operated mining industry. Aitik is more than a gigantic open-pit mine. It is a place where humans use data, explosives, and machines weighing thousands of tons to extract metal that is almost invisible within the rock. Yet every ton of copper leaving the Arctic also leaves behind a mark that cannot be erased immediately. The electrified future may be brighter, but the road leading to it still passes through landscapes that have been excavated, crushed, and reshaped. Do you think technology can make mining truly sustainable, or does it merely reduce the price that must be paid? Leave your thoughts below, like the video, and follow Mandarin Tech as we continue exploring the machines quietly keeping the world in motion.